All right, welcome everyone. It's such a pleasure to have you all here. And we have these wonderful speakers today. And the first speaker is Dr. Kyung-Sik Yoon of JPL. He's going to tell us about AI in space exploration. Now, if you have any questions during the talk, use the chat box and write down a few words so that you can be in the queue for the Q&A. Or you can raise your hand using the reaction button at the end of the talk. At that point, you can unmute yourself to start talking, right? And I'm not going to go, read through all the bios since they are available on our webinar posters. But so let's welcome our speaker and give a round of applause.
Thank you. Thank you for the introduction. Can you hear me well?
Yes.
Okay, great. Hello, I'm Kyung-Sik Yoon. I work at JPL, developing technologies related to space exploration using artificial intelligence and machine learning. Yeah, thank you for the kind invitation, and yeah, let's get started. What I would like to talk about today is how machine learning and artificial intelligence are being utilized at JPL. I have been working at JPL for about 8 years, and during these 8 years, I have noticed significant changes in the internal perception of machine learning. Traditionally, there have been 3 major challenges in applying machine learning and artificial intelligence in space exploration. Number one, statistical property and uncertainty. There has been skepticism about the advantages of machine learning compared to traditional rule-based systems. Number two, computational burden. It has been challenging to run machine learning and AI algorithms, which require significant computational resources on usually limited hardware for space applications. And number three, conservative nature of space exploration. There is a tendency in space exploration to avoid changes unless there is a problem. So recently, however, there have been some changes driven by a few major reasons that I will address step by step today. Firstly, and most importantly, the complexity of space exploration is increasing significantly, making it difficult to carry out missions with traditional rule-based systems. Let's watch a video to illustrate this point. So NASA and ESA, European Space Agency, are collaborating on an ambitious mission to bring Mars rock samples back to Earth. This video highlights key moments of the Mars sample return campaign, showcasing the process from landing on Mars and collecting samples to launching them off the surface and returning them to Earth. These samples, these are the sample tubes collected by the Perseverance rover, could provide crucial insights into the possibility of ancient life on Mars. So the rover, the Perseverance rover, has been operating since 2020, collecting samples in the sample tube. And that's the MAV Mars Ascent vehicle that is to be launched to the Mars orbit. And on the Mars orbit, there's sample caching system to receive the sample and send back to Earth. So this is quite a complex process. And also, what is really exciting is that this is the first rocket launch outside of Earth. So that's an exciting first. So this is the Mars sample return mission, and again, it's quite complex. As space exploration systems become more complex, Autonomy is no longer an option, but a necessity. With communication delays between Mars and Earth ranging from 10 to 20 minutes, real-time control is impossible, thus requiring advanced autonomy. So at JPL, we focus on several key areas. The most important aspect is how to make onboard decisions in uncertain, unknown environments where real-time communication with Earth is not possible. So as I mentioned earlier, space exploration is traditionally conservative. However, as missions become more complex and the need to explore new environments grows, the demand for new technologies increases. For example, the Ingenuity Mars helicopter is a good example. Due to the communication delay between Mars and Earth, the drone operating on Mars must move autonomously. Considering weight and performance criteria, the traditional FPGA or RAS-750 processors were not feasible. Therefore, for the first time, we applied Qualcomm's Snapdragon 801 mobile processor, which is similar to the chip used in the 2014, 2015 Samsung Galaxy smartphones. There were many challenges in adopting a new processor, especially a mobile processor for space missions. Would a mobile processor work well in extreme Martian conditions? Compared to processors that have been verified over decades, there was inevitably a lack of data in the mobile processor side. Therefore, the Ingenuity helicopter was included as an additional mission under the title of technology demonstration. What were the results? It was actually a tremendous success. The initial goal was to survive for 30 days and complete 3 flights. However, since 2021, it has completed 72 flights over 3 years so far, with the Snapdragon mobile processor functioning without issues. The general purpose processor, which is a Snapdragon, supports Python and also TensorFlow Lite, enabling some various deep learning based object recognition, targeting, detection, and tracking. With recent advancements in AI and computer vision, higher performance hardware is being applied to space exploration. I think this is a really exciting moment, and this is a new beginning to apply advanced hardware, opening new opportunities. So now I would like to introduce some of the development projects I'm working on. How can we use artificial intelligence to explore more efficiently? How can we accelerate development in terms of software and testing process? And how can we automatically detect anomalies? How can we develop low power, high performance main processors? Instead of sending a single main system into space, can we combine multiple systems to reduce costs and mitigate mission risks? These are the topics I will be addressing today. First, there is Aegis. It is object recognition and segmentation software used in the Mars rover. So far, Mars exploration has progressed very, very slowly. Do you know the speed of a Mars rover? It is 150 meters per hour, which translates to only 2.5 meters per minute or 4 centimeters per second, which is 1.5 inches per second. It goes really, really slowly. There are various reasons for this, and exploration, safety for the exploration is paramount. That's the most important thing. And therefore, rover path planning is done from Earth, and exploration is conducted while avoiding specific terrains. When the rover encounters target terrains identified by geologists, it stops to collect data. The more we can automate this process, the faster and more efficiently we can explore target terrains. Such a system uses AI algorithms to analyze sensor data, interpret images, and make decisions, reducing dependency on ground control. Since 2012, the Curiosity rover has been using Aegis to traverse Martian terrain. Give me 1 second. Give me 1 second. Sorry. Yeah, let me mute. Yeah, sorry, my 4-year-old daughter just woke up and came by. All right, let me see the next page. Due to the limited time and resources available for operations on Mars, the key achievement has been improving the science return rate from 24% to 94%, as you can see here, by using this automated target detection, feature extraction, and filtering type of a system. And next is about our SLIM effort, which stands for Software Development Best Practice. Software is becoming increasingly important in all areas, including algorithm development, testing, and management. Since it's not developed by a single person, it's crucial to follow specific guidelines during development. So we built best practice guidelines. So does anyone enjoy writing test code? Probably not. I prefer creating new features and brainstorming new ideas, but testing code, that's not very preferable. This project began with the question of how to automate writing test code. It's also open source. You can take a look at the website. Everything is publicly available. And yeah, we use the robot framework to automate the testing code generation in combination with large language model. So we can see that the recent advancements in large language models have significantly improved the quality of automated test script generation. This is a recent paper that quantitatively compared several large language models with manual test code. So you can see that generated test code often requires some developer interventions. After fix, there's some improvement in the compilability. Okay, and next page, I prepared a quick poll. So this is example. On the left, we have a simple calculator that performs division, multiplication, and addition. To verify that this code works correctly, we have two test codes, 1 and number 2. One was written by a human and the other one by AI. Can you tell which one was written by AI? So I made a quick poll. Which one is generated by AI? Let me reshare the link on the chat here. Okay, great. Yeah, so it's a real time. So if you made a poll, then you can see that. Let's wait until some 10 people vote for this. Okay, that's great. 8 people voted at number 1, and 3 for 2. And that's great. Let me go back to the slide. So let's reveal. So the AI generated code is number two. So many people, some people guess right. So the point is that it's not this indistinguishable. It's actually indistinguishable in terms of quality of code generation. So it's quite impressive. Here is an example of generating unit tests. It's incredibly fast. You can achieve this speed even on your laptop. And taking it a step further, for generating more complex code, we recommend that we believe that it's beneficial to include an intermediary step of generating pseudocode using robot framework. So here's example. And AI is also used for deep space network data analysis. This system is called TAPAS, Track Augmentation and Performance Analysis System, which automatically and efficiently detects anomalies. The DSN is a system for deep space communications. It consists of 3 antenna systems on Earth with data analysis conducted at JPL. It also supported the Danuri KPLO, Korean Pathfinder Lunar Orbiter mission. I was at the California Goldstone Complex observing, supporting Danuri KPLO communications, and it made me proud as a Korean. This is a view for the DSN California Goldstone Complex. Operators are constantly struggling with information overload. Our track visualizer, which we developed, is currently being used in DSN operations. Not only is information overload a problem for each DSN operator, but the excessive demand on the entire DSN system is also an issue. The system is already overloaded, and with the increasing number of satellites and deep space missions projected after 2030, this overload will only worsen. So how can we solve this problem? There could be a few options. Number one, enhancing onboard computation for each satellite to minimize communication data size. Number two, increasing DSN hardware infrastructure. That may be hard because of funding limitation. Number three, automating the DSN anomaly detection on the software side improvement to quickly identify and resolve issues, minimizing downtime. This could be a realistic solution. Additionally, there is a game-changing opportunity with DSOC, Deep Space Optical Communication, which is currently being tested. It successfully uses laser-based communication, offering speeds more than 100 times faster than traditional data bandwidths. A recent article reported successful data transmission at 200 megabps, which is sufficient for 4K video streaming in space. This is quite impressive, I think. The TAPA system we developed analyzes high-dimensional real-time DSN data to perform data compression and anomaly detection. I do not have time to explain more detail, but I hope I have a future opportunity to explain more. And multivariate heterogeneous data processing, that's my primary research focus. And the DSN TAPA system I mentioned earlier is part of this research, and this is another one. The multivariate time series algorithm can also be used to address geoscientific problems. California Central Valley is a major agricultural hub in the United States. However, excessive groundwater usage over the past few decades has caused severe landslides. The land subsidence. The subsidence level is more than several tens of centimeters per year, so it's significant. So we conducted a project to predict subsidence by analyzing precipitation, groundwater, and geological structures to manage groundwater usage. Each data type has different spatial temporal resolutions and noise levels, which adds to the prediction challenges. The primary goal of this research was time series prediction, but we discovered something more interesting here. We found that geological composition, which was previously measurable only with in situ sensors, could be indirectly calculated using INSAR-based remote sensing satellites. This opens the possibility of quantifying geological structures with satellites, eliminating the need for expensive and cumbersome in situ on-site sensors. Although this was not our initial research objective, it led to unexpected finding. I believe this is quite a beauty of research. This study was selected as a technology highlight by NASA JPL. From an onboard autonomy perspective, NASA is focusing on developing the next generation brain for space exploration. So the current system, RAD 750, is retiring soon. And Qualcomm's Snapdragon showed promise on the Mars helicopter, the drone system, but due to limited disclosure of its low-level hardware validation from the company's IP, it's not ideal for future major missions. NASA is now developing a new system based on an open source architecture called RISC-V. It excels in radiation tolerance, performance per watt, and fault tolerance. So it supports AI, vector engines, and FPGA fabric, enabling large-scale parallel processing compared to existing ones, and use of various deep learning algorithms on board. So this is another exciting opportunity that can be applicable, and we might be able to use currently developed deep learning algorithms on board in space. Lastly, multi-agent systems are becoming more popular. Instead of relying on one big system for missions, we can use many smaller units. If one fails, the others can still complete the mission, reducing risk and cost. However, the disadvantage is the complexity, increased complexity. Planning motion for multi-agent systems requires complex convex optimization, which is computationally intense. To solve this here, we first used machine learning for initial optimization, then we refined the results with convex optimization, the mathematical solution. So we use this hybrid approach to solve this efficiency and accuracy sort of a trade-off problem. In 2024, sometime this year, the CADRE multi-agent system is set to launch to the moon. It consists of 3 small rovers equipped with ground-penetrating radar to image underground geological structure. So these rovers will communicate with each other to create a 3D map of the moon's geological structure. So yeah, we have 3 rovers, and they communicate among each other and imaging underground. So let's summarize. Where do future opportunities lie? I believe there will be opportunities in computer vision, detection, segmentation, object tracking, classification, especially with the development of the new RISC-V architecture for high-performance space computing system. There will be increasing demand and opportunities for onboard computer vision systems. Also, how can we maximize cost efficiency in terms of flagship missions? The multi-agent field is still in its early stages. It's worth thinking about how to reduce mission risk using this sort of multi-agent approach. So that's all for today. Thank you for listening.
Thank you. Fantastic. Wow, your 4-year-old is lovely. And You okay with the challenge pretty well. All right. So are there any questions? So Daniel, go ahead.
Yeah, hi. So thank you very much for the
Yeah.
presentation. I just had and I'm glad that you brought up space optics because it's a little bit related to what I will discuss in my presentation. But my question is, if I understand it correctly, there are many benefits to AI on Earth, but in space applications, due to limitations in hardware, the size of the hardware and the computational power that it can do, you want to task missions, actions with through AI so that when it's not communicating directly with the humans, it's able to not have as a lower downtime as possible. So my question is, can you remind us roughly what's the time that it takes to communicate between the Mars rover to Earth?
Yeah, it's 10 to 20 minutes depending on the orbit location, relative distance. So yeah, it's quite significant. Yeah, it's really hard to deal with sort of a real-time communication or real-time joystick type of navigation or instructions. So there should require some autonomy. But so far for the Mars rovers, you can always stop and think and wait for 20 minutes. That's possible, but yeah, in the future for other applications, for the even on Mars, for the yeah helicopter application or drone application, uh, that requires real-time changes and adaptation, and also exploration to other planets such as Enceladus or Europa, which has the vast ocean worlds. In that case, we need a system that navigates underwater. It's underwater submarine type of a system that requires a high level of autonomy that adapts to the environment, and you have to float around. They cannot wait for the instructions from Earth. So that's the challenge, and that's the opportunity that we can leverage so that we can apply some of the advanced autonomy algorithms for future missions.
Okay, thank you.
All right. Do we have another question? I thought somebody. Jung Yun Bae, please go ahead and open your microphone to ask a question.
Hi, I'm Jung Bae from Michigan Tech, and then I'm the roboticist working on the multi-robot systems, trying to extend my field to the space robotics. And then as we're seeing the opportunity slides, I was wondering, is there any like particular NASA programs that like university professors or research teams can apply for autonomy for the multi-robot systems? I know we had Luster's program last year, specifically targeting for autonomy for multi-robot systems, but I was wondering, in general, is there any other programs that we can apply for?
Uh, I do not know the specific program, but I think it's a good start is Cadre. You can start from Cadre
Okay.
from JPL, and also recently there is a call for re-architecting the Mars sample return. So I'm not sure if you are familiar with it, but yeah, you know the recent funding restrictions regarding the Mars sample return mission. We are kind of thinking from scratch and calling some help to the open academia and industry partners to address the issue of returning samples back to Earth. How can they be much simpler, faster, more efficient, and cheaper? So in that regard, I believe there should be some opportunities in terms of systems engineering or re-architecting or any multi-agent opportunities. I hope
Thank you
that
so
helps.
much. Yep.
Okay, so we will probably continue to take this question by this chat box. But for now, we should take a photo. So let's open your camera and Edie Park, please go ahead and take a photo.
Yes. Okay, so let me take a picture. So please turn on your camera. Okay, thank you. Yeah. Just okay. So thank you so much. Okay. No, I'm not done yet. So please turn on. So I'm just waiting for the others to turn on the camera, but I think we need to just take a picture right now. So okay. Okay. 3, 2, 1. One more time. 3, 2, 1. Thank you.
Thank you. All right. So let's then move to the second talk, and we can have further discussion if there are more questions later after the second talk. All right. So thank you very much, Dr. Yun. That was fascinating. All right. So the second talk is, let's welcome the second speaker now, Daniel Warren. Is the Vice President of the TICWA. And he's going to tell us about another fascinating title that is shedding light on Li-Fi, revolutionizing secure wireless communications for aerospace and defense. So let's give a round of applause.
Hey, thank you. So just before I get started, just a quick introduction. My name is Daniel Warren. I was adopted to a family in Massachusetts when I was 11. I was born and raised in Norangjin area of Seoul. And so I grew up in Western Massachusetts. I was born and raised in Seoul till I was 11, and I grew up in Massachusetts. Long story short, I went back to Korea for the almost past 14 years. Started a family there. I have 2 young girls, 11 and 9. And my past 12 years or so has been dedicated to space and aerospace and defense industry, mainly on the strategic partnerships, marketing, and business development. I'm thankful that I'm part of the team at KASSTA. My future mission that I spoke to Dr. So about is trying to introduce different types of companies that are in the aerospace and defense areas that could come and speak and be introduced to our association to kind of give our members a better understanding of what type of applications that there are for your technical background expertise. So Dr. Yoon just talked about his specific focus on the research type of things that JPL and he's involved in. Hopefully what I'm planning to do is to kind of bridge the gap between the research and what can actually happen commercially. Because in a perfect world, society would have unlimited funding for scientists and researchers to really push the boundaries of the human understanding. Oftentimes, if there is no business case for it, it becomes difficult to sustain that type of a mission. So I think it's important to balance out how our community can take the technical knowledge and all the engineering efforts and the science behind what we do and see how it can benefit both humanity on Earth and also in space. So with that in mind, I just wanted to quickly, there are many things that my company does today, but I just wanted to quickly kind of focus on one specific technology that we're working on, which is Li-Fi. So let me just kind of quickly go into the presentation. so that the attendees today can have a context of what we do. So we are a tier 1 supplier to commercial and defense aerospace today. We were founded in Toulouse in 1917. That's 1 year after Boeing was founded. This is the gentleman who founded our company, Pierre-Georges Latécoère. Latécoère is just like William Boeing, it's a family name. And he was one of the pioneers in building and designing aircraft. As I mentioned, we began in 1917. Throughout the early years, we were one of the only few companies in the world that was capable of building aircraft. And by 1922, because we believed in what we were doing, we were also the world's largest airliner. We're the first to create commercial routes between Southern Europe and North Africa, and eventually also to South America as well. So we just celebrated our 100-year anniversary in 2017. And in terms of our company size, we're a quite small company compared to, let's say, Boeing or Airbus. But you can see how big the aerospace industry is just by kind of looking at a smaller company like us and what we represent in terms of revenues. These revenues are relatively lower due to the COVID impact. We were up to 800 million a year before COVID, but not just because of the COVID, but because what COVID represented in terms of production rates. Meaning the number of aircrafts that could be built per month by Boeing and, let's say, by Airbus themselves. Most aerospace industry right now, we're in recovery mode to get back on track. This is kind of a snapshot of type of products that we are shipping just in 2023. As you can see, we are the world's, we build the doors for commercial airplanes. For example, on the Boeing 787 aircraft, that is our design that we worked with Boeing on. And we're also manufacturing the doors. We do structural work and we do electrical components, some avionic onboard equipment, and we also work on quite a bit of satellite wiring activities. And these are some of the companies that we work with across the spectrum. And roughly from a company perspective, this is the split between our aerostructures division and the interconnection systems division. And the good news is we are hiring. So and which is another mission, which is another important mission of KASSTA. So the aerospace and defense right now, as I mentioned, as we're in the recovery mode, we are actively hiring, and most of our hiring is coming from the engineering side as well. So if any of the members on the call today who have a background in these types of engineering, these are not just for my company per se, but across the aerospace and defense sectors. These are highly skilled jobs that we're looking for today. And this it's a quick global snapshot of either our manufacturing sites or our offices. But most of our design today, it's in Europe, and our job is to start to grow more of a presence in the Americas as well. Okay. One of the key successes of our company has always been related to our research and technology division, which, as you can see here, we're missing JPL and we're missing NASA, and perhaps in the future state we can kind of add this in. This is where it becomes really interesting. As an engineer or as a science background professional, you don't always necessarily have to work with a commercial company to be involved in the commercial sector. And as a commercial company, it's very important the type of work that we do with government agencies intergovernment agencies to really drive business cases and also to make the world a more connected place. And today, there's a big focus in the marketplace today on what we call the next generation aircraft. So as you just saw, the aviation industry, we just roughly finished what we call the first 100 years. And the industry right now, we're really looking forward to the next 100 years. And the next 100 years is really driven by sustainability. And if you see a lot of the technology breakthroughs that's happening, whether you're involved in propulsion, let's say engine design, to airframe design, to even the types of fuel mixes, it's all being driven by trying to make things lighter, but also to make sure that these lightweight capabilities it lives up to the safety standards that the aerospace industry is very famous for. And these are kind of some of the different engineering efforts that we're involved in to contribute towards the next generation of the aircraft. And with that, I'm gonna go into our efforts on Li-Fi. Our company's Li-Fi efforts has now been over 7 years. And I believe it was in 2008, there was a gentleman by the name of Professor Haas. He's a professor in Scotland, and he gave a TED Talk. And in that TED Talk, rather than using a wireless Wi-Fi access point, he demonstrated in his talk a Skype video call using light. So what does Li-Fi mean? It's an acronym for light fidelity. And unfortunately, it's not a perfect word because it's a borrowed word from wireless fidelity. So another way of kind of looking at this, it's a wireless communication, and rather than using RF rather than using the radio frequencies that we know today, we're using light. Professor Dr. Yoon, in an earlier just before the presentation, he spoke about space optics and how it's using laser. So laser would be at a much higher level. What our company is using today is near infrared. And one of the biggest reasons that we're using near infrared is it has to do with safety. So as you know, lasers can be quite dangerous, whereas the near infrared spectrums that we're using, you can look directly into it. It's always on, it's non-visible to the human eye, and there's no electromagnetic field. So there are certain benefits that this unlocks. It's safe and it's fast. So the speeds that we're talking about at the distances that we're doing right now is we can get up to about gigabit of transmission of bandwidth. We're extremely secure, meaning unlike the traditional radio frequency waves where you are able to spoof or spy on that signal, and then to be able to then decode the data transmission to see what's going on. This particular Li-Fi technology makes it extremely difficult to do that. And the number 4, what's interesting about number 4 is, again, it's not just about how good the technology is, it's why would the consumers or the customers want to pay for that technology. And one of the big reasons is for a commercial airliner, let's say if you're Korean Air, if you can make money not just selling the seats on a flight to take a passenger from point A to point B, but make additional revenue, let's say by selling goods on board, right? We see every time we fly on a plane today, we're always trying to buy something on board. This is what's known as an ancillary revenue stream in the airline industry. And the types of entertainment that you offer could unlock additional revenue streams for the companies, but also it can create an environment where customers chooses to fly on your airline because you have better entertainment. And point number 5, lightweight. This is important because there's a specific cost calculator, let's say per every gram onboard an aircraft or onboard a space launch vehicle, that translates directly into the operational cost. So the lower the cost, the better, but also fuel being the largest weight contributor oftentimes, lowering the weight of the aircraft allows you to maximize that fuel range and agility, backbone resilient. What this means is there are multiple different types of existing wireless communication from satellites, for example, whether it be SpaceX, which is a low Earth orbit that's operating on Ka band, to medium Earth orbit operators, could be either Ka or Ku band, or the traditional geosynchronous satellites, which is either multiple bands. So what we are doing is we don't discriminate. We're agnostic on that side. We are connecting the connectivity at the very last mile of what we do. So essentially what you see here is you have 2 optical sensors that creates the uplink and the downlink. And the easiest way to kind of describe what we do is we manipulate the intensity of the light, where the light will dim and brighten at a rate that we can't detect with our human eyes. But with these optical sensors, it's able to then convert those dimming and brightening of the lights into zeros and ones, which then gets converted into a data signal. Just to kind of give you an illustration, just on the eve of COVID in October 30th, 2019, there was an Air France flight from Paris to Toulouse, and Toulouse is where our headquarters is. We took a Airbus A321 aircraft, and we converted the first 20 rows of the aircraft. And we had gamers from all over Europe that competed to be part of this first flight. And the gamers were able to play a racing car game with each other on board the flight from Paris to Toulouse as a technology demonstrator to show the benefits of it. So where can light-based wireless communication be used? It can be either commercial or corporate, military and airlines. So on the commercial side of it, one of the main drivers on the commercial side is reducing the weight. There are kilometers of wires. There are miles of electrical wires, which are often heavy because of the metal content inside of them. And if you imagine every seat that you sit in on an aircraft, there's wires that are connecting every seat to provide power, but also the data. Some of the newer technology makes it lighter by creating more Ethernet cable-based systems. But regardless, the challenge remains where there's a lot of wires and it becomes very complicated to certify. And this is where we believe that using a light-based transmission system to onboard the commercial aircraft could be of benefit. In the real world today, Delta Airlines, I would say, is probably a world leader from a commercial airline point of view. Delta has developed their own wireless system using Wi-Fi access points to provide media content, the in-flight entertainment content to all the seats. The issue that Delta is having right now is the traditional wireless access points. The bandwidth on board the aircraft, it's limited. So the passenger experience it's not what they want. So today on Earth, we're looking at things like 4K media. We're also looking at things even up to the levels of 8K, very, very ultra high definition. quality displays and monitors, especially from Korean vendors. These are type of experiences that when you are in flight, you can't experience because of the limited bandwidth. So my company today, we have been talking with Delta to try to potentially offer our Li-Fi system rather than using the onboard the Wi-Fi access points. So today I was on an American Air flight from Phoenix, Arizona to Philadelphia. It was roughly a 4 hours and 20-minute flight. And on that flight, American Airlines, for domestic flights, they do not have any monitors on their seat backs. So what they rely on is bring your own device, and they have a very nicely designed in-flight entertainment application that when you're flying, you can watch some of the newer movies or the different TVs that we all know. One of the issues is on a flight, let's say you have a flight that has 190 passengers on board. If all 100 people got onto that entertainment system using the Wi-Fi access point today, and they all try to watch content, which you're gonna see a glitch. And oftentimes when you're flying and you're unable to access the media content, it's related to the fact that the current technologies on board, it can't be as strong as it is on the ground. So on the ground, you can have Wi-Fi 6, Wi-Fi 6 Plus. Now you're seeing Wi-Fi 7 protocols come on. Unfortunately, when you are flying in this type on an aircraft, you have to be really considerate about a lot of the onboard avionics and onboard instrumentation that makes the pilot safely fly the aircraft, and you don't want a radio frequency interference with those mission critical equipments. So it creates so Wi-Fi naturally has a bottleneck issue, and those are the type of things that we're trying to solve on the commercial side. On the defense side, this is where it kind of becomes quite interesting, where traditionally the flow of technology from has always been, it was a secret project within the military industrial complex. Then it becomes proven, tested, and then it becomes commercialized. I think one of the best examples of this is LASIK eye surgery. The core technology behind LASIK eye technology was in fact from laser-guided missiles. So the technology that allowed the laser-guided missiles then became the same technology that allows the doctors to operate on your eye with extreme accuracy. So traditionally that's been known as a spin-off. Now what we're starting to see is a spin-on, where especially in the geopolitical situation that we're in today, the war in Ukraine is an example of this. You're seeing a lot of commercial technology that's been flipped out and being used now on the defense side. However, there are challenges in the defense, and security is one of the most critical elements of it. This presentation, interestingly, was something that was targeted specifically for Korean military at the time. So just a quick side note, before I joined Latticor, I was working for a company in South Korea based in Songdo, the Free Economic Zone in Incheon. The name of the company was Huni Technologies. And Huni Technologies and my current company, Latticor, we made a strategic partnership to bring Li-Fi to the commercial and defense markets. And Latticor decided to focus more on the commercial market, whereas the Korean company decided to focus more on the defense side of the market. And what you see here is, as we all know very well, Korea is for all intents and purposes still in a state of war. And because of this, we know that there's quite a bit of resources that are being allocated to the defense of South Korea. And there are many of these type of command, and C2 is command and control type of tents. And traditionally, all of these types of tents are connectivity is the most important thing. Its main job is to get information so that it's able to, so that the commanding officers is able to make mission critical decisions. Traditionally, when you are setting these types of tents up, no matter which army from the world that you're in, it's measured in number of days or tens of hours. Mainly because you have the soldiers carrying all the wires that are necessary to be able to connect all the servers to the routers and to the networking equipment to be able to drive this type of communication. And what Li-Fi does is it removes a lot of the weight plus the speed to set up. But more importantly, in defense applications, traditional wireless communications that we know today and we enjoy today, it's illegal, mainly due to cybersecurity. It is possible to spoof or steal signals, RF signals, as I mentioned before. And with a Li-Fi system, it becomes nearly impossible to steal that signal, because if you are not under the beam of light, you don't have connectivity. 1, 2, your device has to have the right hardware dongle that allows it to communicate. And 3, the governments around the world can further add on their security protocol at the access points. So the U.S. Army European African Command, they have fielded this technology using another company's solution, and this is not something of science fiction that will come some years from now. This is a technology that's ready to go today. This is another kind of a simulation of creating really rapid connected desk areas or sites. This is a simulation of a bunker. In South Korea, we have a large number of bunkers that's distributed throughout the peninsula, and the reason's very simple, as you can imagine. In case of a war, we have to have these sites that are protected deep underground, that allows the commanding officers and the leaders of the government to conduct the war effort. However, the cost of keeping all of the bunkers active at all times, it's extremely cost prohibitive. So in Korea, what they normally do is these bunkers are empty normally. The key bunkers are always staffed, let's say, but there are many of these types of bunkers that are empty. And during different exercises throughout the year, they go in and set up a complete, let's say, a network operations center from scratch, so to speak. So in these types of situations, then rather than having to deal with hardware, constantly upgrading hardware to the latest protocols, we're able to create these kind of tripod systems to be able to deliver very secure wireless connectivity to the warfighters. And as I mentioned, what's really for us, what's really important is that we are not concerned about what is the main communication backbone, what kind of satellites that we're using, or what kind of terrestrial signals, because at the end of the day, our technology is only dealing with the last mile of the communication. So what this means is that it's also cost effective, because one of the things is that when you are using different types of modems and different types of satellite connections, then that kind of adds on cost to the ground infrastructure as well, and we're trying to reduce as much of that. Another usage case of the technology is inside of moving vehicles. For example, this is inside of one of the newest Korean small, you can think of it as a command and control tent, but on wheels. And you're also able to now give wireless connectivity to the warfighters. what happens today is you have to be physically wired in, and you can imagine in a small confined space as you're moving, it makes it much more difficult to do. This was something that that we had discussed because at the time we were working with another government's project. This was a simulation of a usage case for the Korean presidential aircraft. In the United States, we would call this an Air Force One. So what this does, so this is kind of a usage case that allows a wireless connectivity where the head of state or different security clearance levels of people is able to go and get the data that they need based on their clearance level. Oftentimes, when the presidential plane is flying, you also fly with the journalists. And now we can provide journalists connection to the World Wide Web, but also the government officials to secure access to government data as well, which is wirelessly, which is a big game changer. This is a naval application. What this shows you is on the Navy side, it's even more critical the amount of electrical emissions that a ship emits, because through satellite technologies or by using certain medium altitude or high altitude drones or UAVs, your enemies can approximate where your ships are located if the ships are giving off electrical signals. So during different battle situations, there's an important concept called emission control. And at the highest levels of emission control, the rule on board an aircraft is to shut off any equipment or any electrical equipment that emits any radio frequencies. So when that happens, it keeps the ship safer, but the downside of that is to communicate on board these ships. Often, I mean, these are very large vessels. You would have to wire everything through to communicate, and you're often doing it through a handheld physical device that is connected via wire. So if you replace this with a light-based system, it has zero emission, which keeps it very safe, but also it gives the mobility and the flexibility to the sailors on board. This is another type of an application. For those of you who are familiar, the airplane looks like an F-35, but it's actually KF-21, KAI's newest fighter that was built indigenous to Korea, the Borame. And this was our technology is not on the Borame. We just illustrated to showcase the application of it. Again, one of the things that I would like to try to bring more to KASSTA is, how do we bring technology to, in the hands of the final user? So oftentimes the technical data to maintain an aircraft or a government asset or even commercial airplane asset, these are highly sensitive. And you are not allowed to oftentimes have it on a laptop or portable devices. So if you are in charge of maintenance, it makes it quite difficult and cumbersome to maintain it because of the security chain, and of course Wi-Fi is not allowed. So when you are able to have now a secure wireless communication, you can set up temporary stations just using very simple portable chairs, stools. And now with the right device, you're able to connect to that secure data. And more importantly, also, the aircraft today, whether it be commercial or military, it's collecting terabits of data as it's flying. And that data can come from things like the performance of the engine, operating temperature, and all of this data then supports, and then it gets it's aided by AI to be able to do predictive and preventative maintenance of the aircraft. And so, except some very mission critical data is often using real-time data relays or satellite backbone to transmit that data back to the ground. However, some of the other terabits of data are saved on board the aircraft, and when it lands, it's unloaded, usually doing a hot swap. So swapping out of solid state drives, etc. What this allows, what the Li-Fi access allows us to do now is, as the plane is parked, you're able to have a way to download all that, download all that mission data from the aircraft to your computer, which is also connected. And also importantly, upload the new mission data or the latest software versions as well. So this was, yep. So that kind of brings to the end of the presentation on, I didn't go into too much of the technical side on how the Li-Fi system works, because ultimately it's much simpler than we think. What was difficult was that before the proliferation of the LED technology, it was very expensive to be able to have a reliable lighting element that can be turned on and turned off, and also the processors that are required to be able to understand that sensing data and to be able to code and decode. So now it's extremely cheap LEDs, and so theoretically, this technology has been possible even at the times of Alexander Graham Bell. The difficulty was the cost to making this technology cheap enough for commercial adoption. And we are in 2024, we're at a place where these kind of have made a really nice confluence to each other. So yeah, so that's kind of towards the end of my presentation. Again, the main theme was trying to connect what happens in technology and research side, and then how we can bridge that onto the commercial side of things.
Excellent. Thank you very much. So let's see. Now, do we have any questions to Daniel or comments? Dr. Yun, you pushed something. Would you like to comment?
Oh. Yeah, someone raised a hand. Jung-Hoon Kim. Yeah, please go ahead.
Yeah, thanks for the nice presentation. And looks like the Li-Fi technology has lots of advantage over the Wi-Fi, but so many of airlines still rely on those Wi-Fi technology even with those limitations. So is there any special reason why they don't kind of adopt this new technology anytime sooner?
Yes, the short answer is it's related to what Dr. Yoon spoke about in his presentation. When it comes to aerospace and space, the reliability, which translates into safety and cost, the cost of it is so high and the focus on safety is so high that introduction of new technologies always takes a lot more money, and it takes a lot more time to go through all the various types of certification processes. To be clear, on the space side, it's a bit easier because oftentimes it's not directly related to the human cost oftentimes. So when you're launching a satellite, for example, SpaceX, Starlink constellation, for example, to give you an illustration, it's an incredible company. They will do a new satellite design roughly every 16 months or 18 months. To kind of compare that to the traditional satellite industry, it would be one satellite and it lasts 15 years in orbit. So they can't fail, it's got to go up. But whereas some of the newer entrants, it's becoming faster, but even then it becomes more expensive. And then of course you have to have a safety. And then the other part of that conversation has to do with Li-Fi will never replace Wi-Fi or Bluetooth. The future will always have Wi-Fi, Bluetooth, wideband, WLAN, and Li-Fi will be a part of it. And the biggest reason for this is as the world goes to 5G and 6G and the subsequent faster bandwidth, it no longer becomes the importance on how much bandwidth you can carry, but it's about latency and the speed. So what 5G really does today is you can have a surgeon that's sitting in Seoul, South Korea. Let's say we have the world's best heart surgeon that's living in Seoul. This person can have robotic operations and do surgery on a patient in London. And for that to be possible, the latency between that control where the surgeon is in Seoul is operating remotely, that robotic arm that is doing that counter movement has to be in real time. And this is the true promise of 5G. It's more of a quality of service. So but you don't always need that type of quality of service. Wi-Fi does the job well. So future aircraft, commercial aircraft, let's say, will always have some Wi-Fi ability, Bluetooth. Li-Fi is just an extension of that. So if you, even on the Apple iPhones today, I think as early as back in 2016, 2015, if you open up the iOS coding, there's a line for Li-Fi that's been built in. And the reason is when the world truly adapts to a 5G, when you go into a building, you're gonna lose your 5G connectivity because of the radio frequency spectrum is not very good at traveling through walls, for example. So then the question is, you as a consumer or as a business, you're paying for a service, and that service means that you're expecting a quality of service. But if you're not directly getting a good connectivity with the 5G tower or the signal, then what happens? So this is why there's a focus on Li-Fi. What my company is doing, we're not doing anything groundbreaking. This technology, it's gaining adoption on the ground first. So our modem partner on our project, it's Philips Lighting. For those of you who may not be familiar, Philips is one of the oldest companies in the world that makes light bulbs. They're the second largest in the world. And Philips's future vision is that every light bulb that they sell will be an access point. And they have a product called True Li-Fi, and they have it installed on over 200 different sites around the world. So if you go to the football stadium in Hamburg, for example, the journalist media room, there's no Wi-Fi access. It's all done by light bulbs that's provided by Philips. So you can see we are following what's happening on the ground and trying to bring that technology into aerospace and into space. Thank you for the question.
Thank you.
All right, great. Let's see. Any other questions? Simon Shim, would you like to talk? Your microphone is open.
All right. So thanks for this perfect presentation. Even though I'm not in this industry, I'm in the civil building industry. I always want to hear new technologies. So for the future of civil engineering can adopt this. I just wonder, not the technical question, I'm just interested in JPL. I think the last speaker also work in JPL, or probably senior speaker in the senior forum, but is there any kind of opportunity for the JPL open to the public so we can visit the laboratory someday? Or is there any kind of open the kind of to the public so that I may take my son, or if I have a chance to visit LA? Is it in the California LA?
Yes, it's in Pasadena, California. And yeah, you can sign up for a public visit through the website, as I know. So yeah, it's open to public. So yeah, you can just make an appointment in advance.
Great. Thank you.
Okay, Soyeon-Yi has a question in the chat box. Can you open your mic and speak?
Yeah, I just wonder, it seems like this Li-Fi technology not that cheap because it's installed in a football stadium for the journalist or airline kind of thing. And when do you expect it can be more affordable that we can install it in our own house or office area?
So I think today you can do it for under $2,000 or so. There are a few companies that do it, including Philips. But it needs to be cheaper. I don't know if you remember. Do you remember the first light bulbs that we knew that changed colors? It was made by Philips, called
yeah,
Hue,
yeah.
Hue. Those light bulbs, when they launched, I think they were close to $200. But now they are imitations, of course, but you can buy the same type of light bulbs for $30 or so, sometimes even cheaper. So it will be on that same cost trajectory. So the reason why Li-Fi has not been widely adopted today on the ground, it's because the true rollout of 5G has been delayed. So I know that AT&T and T-Mobile and Verizon says 5G, 5G, 5G. It's very rarely it's an actual real 5G.
You're
So
right.
it's sort of a marketing term. So, but it's coming. When 5G truly rolls out, there's going to be greater pain points for this, and you will see the cost coming down. But if you have a couple $1,000s and you're curious, you can install them yourselves too.
Ah, okay, thank you.
All right. I don't see any more hands up. Or do we have anybody to comment? No, if not, all right, let's then close this session by thanking fantastic speakers and excellent audience today. Thank you, everyone.
Thank you.
Thank you.